Hello and welcome back. To put things in perspective, in the previous video we had been looking at static optimizations. Those are optimizations which can mostly be baked in one time at the beginning, and they were pretty good. They sped things up a lot. But still, a map is a very fixed thing. So there's no reason really to have so much overdraw for what we're doing. With that in mind, I'm going to go through 3 more techniques, and these will be in increasing level of complexity and time to implement, to be honest. But let's start off. So, backface culling. Let's say that we've got our blocks for our walls, and we've judged when the blocks are right next to each other and eliminated those in-between walls. But just because a block has got its overlapping walls eliminated, that doesn't mean that every wall on the block is going to be facing towards the player. So what we're going to do is we are going to define a normal vector for every wall block possible, and we're going to take in the player's position, and then on the update of the render we're going to do a test to check that the wall essentially that we're drawing is facing towards the player. So let's get into that. We'll go over to our render system and we will store the player position, and then down below when we define the models we will define the set of normals. So what I'm doing here is, if I look at each of these edge tables, they sort of, each of them has a fixed direction where all the coordinates are facing the same way, and I'm taking that as my normal vector and normalizing it. Did I do that right? No, that should be negative. And then in the case of the ground, I'm actually going to be doing the opposite of that. Technically, probably don't need to define normal vectors for the ground because I'm not using that for backface culling, but I take that back, and for that reason I won't do it. Why not? I was just thinking because we may need normal vectors later on for reflections of objects, but that is not the responsibility of the renderer. So with that being as it is, I'm then going to go down to the draw wall function, and inside that draw wall function there's a number of, there's a bunch of variables which are going to be the same no matter what. Basically the direction vector from the position we're drawing to the and I realize as I write this that it's probably not accurate to have a single position for everything, but it's been working so far, so I'm going to do it. There we go. So this is just giving a normalized direction vector from the position I'm drawing to the player. As I said a second ago, not 100% accurate, but it hasn't been causing any issues so far. Okay, so then we go to our rendering face by face, and the first thing I'm going to do is the mask check because that's pretty inexpensive, and then the next thing I'm going to check is whether, according to backface culling, the face is visible. So the way this works is I'm going to take the dot product of the direction vector to the player and the normal. And because this is actually, the direction vector to the object from the player, in this case, my success is that the direction vector to the object and the objects normal are pointing opposite to each other. In other words, the angle between them is obtuse and the dot product will be a negative value. This is just down to how I sort of set this up. It might make a little more sense to take the direction vector to the player than have the dot product be positive, but this is what it is. Okay, so what I'm doing here is I'm also simply saying, okay, if I've got an object and it's really close to the player, then it may not be numerically stable to normalize that direction vector, in which case we simply keep track that that has occurred and just let it go through. So if an object is close enough to the player, we just draw it, that's fine. Okay, but anyway, that's my backface culling here. So I have the setup for my backface culling and then the backface culling itself. Let's give it a go and see what happens. Perfect. Okay. Float object cannot be interpreted as an integer. ND versus array. There we go. That should be fine. So you'll note that the number of draw calls is now slowly changing, but on average we've eliminated about 100 draw calls, which is pretty good. And our frame rate, our frame time, is down to between 11 and 12 milliseconds. So I'm pretty happy with that. We can pop this in, we can say, alrighty, 346 draw calls on average. I'll call it 11.5 milliseconds. Okay, view cull. So the concept of view culling is that if I were to look at my map from the top-down view, there's a whole bunch of like floors, for instance, and basically all the floors are getting drawn, and all the walls as well. But what we should be doing is restricting the set of visible objects to everything which is in the camera's field of view. So what I'll be doing is I'll be taking in all of the visible objects, and then I'll be only recording draw commands for the positions which are within our field of view. So I'll go over, and I'm actually going to do this in the world, and I'm actually going to do it as a separate function. The reason for that is that later on I'm going to just in time compile this function to keep it super fast. So what I'll be doing is now, because instead of having a fixed number of draw commands, we're going to have a variable number, I'll make this function return the number of draw commands which were recorded. And this also means that the renderer is now going to need to know how many draw commands to issue. So it's probably a good idea to actually set this field within the component registry so that the render system will have access to it. There we go. This is storing the number of draw commands for each of these. I'm still going to, I'm still going to record the draw commands and the floor commands, even though I'm not going to use those results, for the reason that this is allocating the theoretical maximum amount of space that we would need if everything were visible. So that's still useful, and it happens at creation anyway, so not a big deal. So what I'll do is I'll just go down to the, where was I? The world, the update stage, just underneath the movement. This should be Z movement, by the way. What am I doing? Because the registry is becoming more tightly coupled to, because the registry is becoming more tightly coupled to the systems, or in the sense that they are reading data and writing data back to it. If we had NumPy arrays, it would be no problem, we wouldn't need to worry about it. But with simple integers, we do need proper references. So what I'll do is I'll just save so that I can later on tell it how many commands it has. So then the way this will be used is we'll go to the render system, and likewise the render system, oh my goodness, this is getting big. The render system is also going to need a reference to the registry, because we're going to need to check the number of commands to draw. So then down in the update, instead of simply running through all of this, we'll go a for loop. Aha, good spot. There we go. Right, so now to actually writing the function. Okay, so what I'm doing here, I'll just get... So what I'm doing here is I'm basically computing the forwards vector of the player. If we were to look at movement, I remember it was sort of strange. We had like this negative cosine and negative sine. I don't know, just experimented until it worked. But the basic idea is for every floor position, we'll want to get the direction vector from the player to the floor, and then get the dot product of that with the forwards vector. Now, as you would remember, the dot product is cosine of theta times the magnitude of those two vectors. And so if the dot product is sufficiently positive, that means that the angle between the angle to the object we're looking at is sufficiently small, sufficiently close to the forwards vector, and that means that the thing is within our field of view. Now, I'm also going to define some threshold, just to be extra certain about that. Okay, so pretty much like I said before, we get the direction vector, take the dot product of that to the camera's forwards vector, and then if that deviation is sufficiently small, then we are within the field of view. In the case that we're within the field of view, we can go ahead and record a draw command for the floor. There we go. Okay, cool. So that's basically what we're going to do. Let's give that a shot and see if that's sped it up at all. There we go. There's always something. Conundrum. Something feels a little off here. So I agree with the close check, right? So the close things are being drawn. The visible things do not seem to be drawn. Okay, back to the drawing board. I'm also going to restrict my camera movement a little bit And there's a good reason for this. It's not just me being lazy. In a level which does not have vertical design, it's aesthetically a little more pleasing, in my opinion, to restrict to horizontal rotation. Anyway, back to the problem at hand. Nice. That is it. Okay, I'll talk a second about what happened. So what I was doing is we know that when we take the dot product of a vector with itself, it gives us the square of the magnitude of the vector. And I was normalizing the vector by dividing by, I guess, the square of its magnitude. Now, this has the effect of not shrinking it to a magnitude of 1, but shrinking it to a magnitude which is potentially a lot smaller, which means that when we take the dot product, it's the cosine of the angle times the sum of the magnitude as product of the magnitudes, which will be really small artificially. So I just take the square root, that gives us the correct magnitude. And anyway, so on to performance. So if we were to just go in a really standardized way and say, okay, that's our view, we've got 294 draw calls, which is not a dramatic decrease from what we had before. But this is now adaptive. So if I were to go and look at a simpler case, we have a lot less draw calls. Still quite a lot, 104, that's a big number. But we can see that the performance is improving. Yeah. Should really be a lot. Anyway, doesn't matter. I guess. Okay, cool. So, but we're not done, because like I said, we can compile this function. So I can go over to my config and go number, which if you don't have number, it's a simple pip install number, but this gives us a lot more performance on our numeric stuff. So I'll go over to this function right up the top and I'll decorate it. Keep losing my main function. There we go. It takes a second to compile. But yeah, pretty decent performance, I guess. So as an average measurement, I'm seeing about 10 milliseconds. But, oh my goodness, I forgot. I'm not doing anything with the walls. So let's go ahead and do the same thing with the walls. I'll go over to my world. And what am I going to need? Position, probably the wall mask, and the wall commands. I'm going to populate. Cool. And then in the render system, we'll do exactly the same thing. So we'll take, yeah, this is fine. Okay, cool. So now I just need to actually implement this function, but it will be very similar. And I'll just keep calling those direction vectors to floor. It's fine. Let me see. I think that's fine. Cool, let's find out. Okay, now have a look at this. This is noticeable. We get down to 5 draw calls from like 100, what we had before. Point something milliseconds. Ooh, that's a little... Probably shouldn't be doing that. Well, again, as an average case, here we're down to 278 calls and about, yeah, between 9 to 10 milliseconds. But you can see that Please don't go. Oh, why are you going dark? Let me just quickly do something. It probably has to do with the last thing that I drew. So if I go up here, let me just go. What's been happening, I believe, is that I draw a wall, and then the color that wall was drawn with was then reused to draw the floor and ceiling. So I just blanket reset it to white and hope for the best. Nice, very cool. Okay, so hopefully what you can see is this is now a more adaptive system, which is what you want. We don't want to have a really big map and then have to worry about, oh yeah, see this is a little off. So I get close to the wall, I can see through it, and that comes down to the threshold. So what I can do is I can go to my function, and for the wall, just set a threshold of 0. It's just a heuristic. There we go. It's still a bit off, but I'm not going to fine tune it too much, because the next technique I'm going to do is actually going to overwrite all this stuff and be way better. But yeah, so I'll just go back and get an average snapshot. Sorry, this has been a little off the cuff today. What's that, like 280, yeah, 283, about 10 milliseconds. Done. Something like that. Okay, now settle in because now we've got the big one, occlusion culling. So what we've got is, imagine we've got all the objects in the world and we've restricted it to all the objects which are within our field of view, but this is not accounting for objects covering other objects. Luckily, we're in a very constrained situation where all those objects are the same size. So it's actually pretty straightforward to check if one object is blocking another, and at the same time to also handle view culling. And the way I'm going to do it is with ray casting. So I'll take the player, I'll cast out a bunch of rays, and as those rays travel along, they will record draw commands for all the new blocks that they see, and when they hit a wall, they record a draw command for it, they register that we've seen the wall, and then they stop. That's their termination condition. So, like I said, this is a pretty big topic. If you're new to raycasting, I would strongly recommend the classic Lode van der Veen raycasting tutorial. The reason for that is it uses the DDA algorithm, which is an adaptive step size algorithm. It's very efficient, it's very fast, and I hate to say it, but I don't really feel like explaining it today. Look at this. This is your source. Look at this. No, that sounded bad, but for real, let's jump in and implement this. One thing I'm going to need is, if I look at my component registry, I'm going to need a mask which indicates all the things that I've visited. This is so that when I shoot rays again over the map, many rays probably will go through the same position, so I just want to check that I'm not re-recording draw commands. Okay. So one thing I'm noting is that the number of arguments in each of these functions alone is pretty big, and definitely it'll get bigger when I bring it all together, because what I'm going to do is, in this function, I'm going to record all the draw commands, not just the walls and the ceilings. So I'm actually going to bundle things together with tuples. So what I'll be doing is I'll be returning the command count for each type of object. Also, just a quick note, if you were to look in the Git repo for this, I've included a version which also writes debug information, And if you go over to the apps update function, you can uncomment some code, comment out some other code to show a top-down view for debug purposes. But I'm just going with for brevity here. So the first thing I'll do is I'll unpack all the data from those tuples. And on the other side, before I call this stuff, I'm actually going to bundle it together. Cool. This gives us a bunch of handy bundles that we can just throw into their function calls. So if we go right down the bottom, instead of recording all this stuff, the first thing I'll do is zero out the visited mask and then record the draw commands. Okay, right, so the render system knows how to consume this stuff and render it. Yeah, I'll leave it. I just thought of something, but I'll leave it for later. Let's jump in and yeah, it's getting a bit big, isn't it? Okay, let's do it. Okay, so what I'm doing is I'm recording info about the origin of the ray, basically, and its direction, pretty similar to what I had above. Just note that X coordinate in this case is going to be the row that we're in, and Z coordinate is going to be the column that we're in. Detail also is the number of probe rays to shoot out. We could probably reduce this even further, but performance I found was pretty good just with this. Okay, so what am I doing here, you may ask? Well, the thing is that the raycasting algorithm is really great at looking forwards, but because I'm using it to determine the visibility of everything, I also need to, by default, take note of where I currently am. So this is just automatically filling in where we are right now. Draw that. And while I'm at it, I'll go ahead and do the same, just in case we start on a wall. Why would we? But we might. Cool. Okay, so this is recording info at the current position. Pretty much what we'll be doing now is we'll be running the DDA raycast, and then for each step we'll be optionally recording some stuff. You'll see how it goes. Like I said, I'm not going to be going into heaps of detail on how that algorithm works, because the purpose here is to use it, not to explain it from first principles. Cool. So far very exciting, but what this is doing is setting up decision parameters and the like for the DDA algorithm. With the DDA algorithm set up, it's actually surprisingly straightforward. Okay, so that's our update. That's it. So now we've got a few cases to handle. First up, we've got that case where our ray is stepping along and it lands on a block that another ray has already stepped on. In this case, what we would want to do is ignore the block and continue. Keep stepping forwards. But it's possible that we've stepped along and then we've hit a wall. So we should probably also check to see, yeah, we've hit something that something else has hit before, but is it a wall? Is it going to stop this ray? And if it has, then basically the current ray is done, right? But in the other cases, we're either gonna, so in this situation, we can pretty much do what we did before. So we're now in a position which has not been visited by any other ray, in which case we can now mark it as visited. And then depending on whether that thing is a floor or a wall, we can act appropriately. If it's a floor, then we record the draw command and keep stepping the ray forward. If it's a wall, then we record the draw command and then we're done. And then, just for safety, I'm going to break at the end. So this is a situation where the ray goes along, it's hit something that it hasn't hit before, I guess, but it's not really a valid thing. So just for safety, I'm going to break. But just double check myself. Yes, we break and then we go on to the next ray, then we keep going. Okay, so I've never felt more nervous about anything before. Well, no matter, I'll just get rid of these functions. Okay, so as you can see, we have almost got it, but things are just a little bit off. Especially like around here. That's not good. It's fast, but it's not good. And it turns out, this was really frustrating, but it turns out that our rendering is biased by a little bit. So what this means is that I essentially defined my positions a little bit incorrectly when it came to building the models. And there's a quick fix to that. What I can do is go over to and just add on a little margin of 0.5. So all the modeling data that I defined up above, the X and Y coordinates are off by 0.5, which means that the occlusion algorithm is working correctly, but the backface culling is sort of causing it to fail or something like that. But anyway, okay, so look at that. Isn't that nice? So in situations where the walls are, oops, that's really not good. I need to fix that. But in situations where the walls are blocking the other geometry, they really truly do block the other geometry. Look at this. 4 draw calls. Okay, now, you might be looking at this and saying, well, this is really fast. This is really good. But if you have any experience of this, you'll know that we can make it faster by just compiling it. Let's give this a go. It takes a second to compile, and then look at that. So taking this as the average case, I'm seeing about 49 draw calls and about 2 milliseconds, sometimes more, sometimes less. and the collision detection for some reason is really off, I'll need to fix that, but I'm going to leave it for now. So have a look at this. Even on 112 draw calls, we're like 4 milliseconds. I mean, that's way better. That's way better than before. I'm pretty happy with that. And this is even without adding doors. Anyway, so probably leave that for now. Look, I hope you enjoyed. It's been a good little project, and I will see you again soon. All right, bye.